For those of you who've been following what we've been doing, this is the second feature release of 2025, and actually the third release of the year if you count the maintenance release that happened partway through the year. It's not a great period of time since the last release, but there's quite a lot to show you. So I'm going to share a notebook here and get stuck straight in. Great. So in terms of the big picture, this is very much a continuing along the direction of travel that we've been showing over the last few releases. So there's no kind of profound new directions here. But for those of you, and I'm pleased to see the poll there that a lot of you have already upgraded, you'll find a lot of functionality that just is building on the things you're already using Wolfram Language for, making it better, faster, and deeper in various different places. If you count new functions, it's 115, so we've been quite busy. But as usual, there's a whole lot of functionality that doesn't actually come with new functions. It just extends existing functions. So it's hard to put a number on the number of the total number of improvements. For those of you who follow me regularly doing these things, I've been doing these new version announcements, screencasts for a few years now. I tend to start from the most general things and work down to the more specific things. But you'll see that through the course of the webinar, we're going to cover all kinds of areas for across different parts of the system, from geometry and machine learning to AI, algebra. But we're going to start right at the surface and the notebook interface and things that have changed. And this is possibly, for those who are interested in dark modes, this is perhaps the most obviously profound change, is that we now have a full support for dark modes. So I can switch between light themes and dark themes. And while on the surface, that's simply changing backgrounds to black and fonts to white, actually to do this correctly, there's every toolbar and dialogue and interface needs considering. The graphics styling, some of these things we've been doing for a couple of versions in preparation have to be considered. The color schemes have been updated a little bit in some of the plots again, just to make sure that they work well in both. And little details like if I'm wanting to prepare things to support both, what do I want to happen to things like the color of a graphic? And I'm illustrating here 3 different choices that I am in control of as a user. I can maintain the color, and the colors have been chosen to try and be good in light and dark. We can do an automatic color conversion to try and guess what a sensible dark mode version of that color would be. Or I can take complete control and say, in light, I want it to be orange, and in dark, I want it to be blue, as I've done with this one. It'll support your operating system choice. It can be done at a single notebook level or as an override and set Mathematica in contrast to your operating system. So all of those details are taken care of. For a lot of people, this is just an aesthetic choice it's argued that dark modes are easier on the eye when you're working for long periods of time. It also has the effect that if you have modern OLED laptops, it actually has a significant effect on power usage as well, to not have to light up your screen if you're working for a long time on battery. So now, completely the opposite end of the spectrum on notebooks, we've been working systematically now for quite a few years of trying to make sure that the notebook is as bound into the Wolfram language as possible, so that it can leverage the fact that we're designing both the notebook environment and the language. And there's an awful lot of ease of use features now that are kind of built in, the kinds of things you see in IDEs coming to the notebook. One small one, but I elevate it here because I particularly love it, is that you're very often in a situation where you're typing something, oh, I forgot to put some brackets around it. How many mouse clicks and keyboard strokes is to put the brackets around that? Well, now you can select content, and I can immediately just type the parentheses, and the open and close is wrapped non-destructively around the current selection. And that goes for all the different bracket types. I could put brackets around that. I can put quotes around that. And it does the before and the after without me having to click to the beginning, typing a character, click to the end, hope to balance it correctly, and type the close. Small feature, but it gets you doing what you're doing faster and with fewer errors, and adds to a whole catalog of such features now in notebooks. Next is really on the input-output side, but I think it's kind of interesting to look at as a kind of notebook interaction, is Markdown support. So now when we, if you select content and do the copy as within Notebook, you'll see that there's this new option, Markdown. Markdown is this sort of standard text-based representation. So if I put that into a text cell, there is the Markdown version of that cell that has various renderers in different IDs to try and look similar, but is in a very simplified human editable text format. And we've tried to work across the notebooks as a whole. So if you limit yourself to fairly basic notebooks, then at a whole notebook level, I can do save as on this, choose Markdown off the list, make a Markdown version of that notebook. Let's close this thing and reopen the Markdown. So if I find the, let's see, all file types or Markdown files, there's the file I just created, and I've round tripped between Markdown on disk back to notebook. So we've got sort of two-way compatibility between individual bits of content and notebooks in Markdown. And since Markdown is a pretty popular format, and it handles very nicely in things like Git for diffing, that's a potentially useful feature for a lot of people. Another feature, and I'm going to I just need to let's see. Let's open a previous notebook I had here so that I can access the menus when I'm in presenter modes. Let's get that one back. And there is a new feature in presenter notebooks. So presenter notebooks are actually what I'm using here to do the main presentation, sort of PowerPoint style, one slide at a time. And if I create a new one here, I can show you a new feature there, presenter notebook. We've always had the problem of when you're editing, you have various slides that can mark up where one slide begins and another ends. So I can have a notebook with lots of slides in it and some content, and there's my slide. But how tall is the slide? Well, it doesn't really matter with text. It'll auto scale if I'm presenting on a screen that's long and thin or short and fat. But with graphics, they have an aspect ratio. So now we have a new capability here where there's the button here that allows me to insert a wrapper for images and graphics. So this is both photos and sort of 2 and 3D graphics. And I can decide the behavior as I go through different screen sizes and screen aspect ratios. I can have it always fit on screen, as wide or as tall as possible to fit, or I can have it full width and it can potentially go off screen vertically. And I can set it to only cover, say, 50% of the vertical height or 50% of the vertical width. So now, even when I've got tall, thin graphics on a very wide screen or vice versa, you can guarantee not to get the graphic clipped halfway through in the present when you jump into presentation mode, and still make maximum use of the screen. So we've all been there. It looks beautiful on your home screen. You go to the lecture theatre, you plug in, and the monitor's on a completely different aspect ratio, and things aren't quite right. That now hopefully is a solved problem. I'm going to switch back here into light mode to continue. Okay, so that's the most general. Everyone sees notebooks. Possibly then the most general when you actually get to computation is data. And there's quite a few things to say that are new in the space of handling data. So for those who haven't been watching the last release, there is a new data structure that we added in 14.2, which is tabular. And the idea of tabular is that it's highly efficient column-based data structure. So when you've got data that is rectangular, very often you get very homogeneous columns where everything in this second column is a date, everything in this third column is a string. And that allows you to then use the power of the compiler to be able to make these things faster and other various efficiency improvements. So minor but important improvements in terms of the data structure involved. You can see it with the tooltip here, but it's easier if I show you by asking for the schema for this database, this data, is that we now have a new geoposition representation. So here's the compiler representation of geoposition. But basically, this column now is optimized for storing latitude, longitude type positions, and will be more efficient in storage and more efficient in operation for that kind of data, which is really the last of the kind of most important data types that you get in these kinds of rectangular data that we didn't support, because we already have good support for numbers, strings, booleans, and dates and times. To go with that, we've also extended the kind of automatic support of tabular. So this tabular I've just imported is the London accidents database that I fetched from the UK government. And I can in a single stroke say, I want to plot just the geoposition column of that tabular as a geolist plot and put all of those points onto a map. So without having to do some kind of take a column, normalize it, then geolist plot of the list, we've now got these data structures joining up seamlessly, and I can just say I want the geolist plot which column of which tabular, and it goes. And this is across several of the geo visualization commands. So I could take that same data and say do a geohistogram to find the density of accidents in London. And for those who are interested, Houses of Parliament is a hotspot, and so is a particularly annoying roundabout at somewhere called Elephant and Castle when I've studied this data. Now, another thing with tabular is that tabular is rectangular data, so it aligns very closely to relational databases. And we also, as part of the tabular project, try to make sure that the kind of operations that you would consider doing in a relational database world are kind of seamlessly supported for kind of just elegant things like joins. So data joining was something that we had before, but we've now generalized it into a much more powerful join. Here's two tables. I've got some locations and names, and I've got locations and populations. And we already had the ability to join across a particular column. So I joined on the locations column. Now, you'll see here that I had three things in each, and they look at a glance the same, but my join only has two. Well, the reason is that if you look more closely, my row coordinates in one data set weren't exactly the same as the row coordinates in the other data set. Typical kind of problem that we're trying to join on things that are not unique tokens that like IDs that match perfectly. So now we have the ability to do joins across any comparison function across any columns. So what I could say here is I want to join those two tables on the locations column, but I want to consider those locations to be the same if the geo distance between the location in one table and the other table is less than 10 miles. So now the exactness goes away, and I can do this sort of fuzzy join, and I get a joined version of those two tables. And the same thing as you would do with a kind of SQL join type operation, but with this ability to call on arbitrary Wolfram language computation to make that decision about whether it's a match or not, instead of being on literal matches. Without this, you'd have to make a version of the table that rounded the coordinates or some other transformation to try and make them the same. Similarly, we have just an extension to joins now to do multi-table joins, so I can join multiple tables 3 at a time with column-wise combine. Here I'm saying join across combinations where the first name and last name can be found in all 3 tables, and I can do an outer version of the same thing that goes to all permutations of first name and last name that match, so all the missings get populated as well. So the equivalent of inner and outer joins within SQL, but again, arbitrary sets of tables, not just pairs that you have to repeatedly join on. Now, tabular is there principally as an efficient and elegant way of processing data, but as you'll notice, its output's kind of pretty. And when we have larger data sets, you've got things like scroll bars to be able to go through the data and storing it out of notebook. So it's got a very nice interface on it. So we're also now starting to build out tabular as a presentational mechanism and as now styling mechanism. So I can arbitrarily style cells in a tabular. So here I'm cycling the columns through 3 different colors. This cyclic actually is a new general computational thing buried in the language, where cycle part 3 will give us the same as part, but cyclic part 4 wraps around to the beginning again. So it just makes a nice elegant language construct for these kinds of things where we're saying we want to repeat the cycle rather than being 3 colors and then white after that. And we also have a couple of conditional stylings as well. So the conditional stylings are item value function and row value function. And the idea of item value function is we can say, I want this color to be, if the number is negative, color it red. So if I want to see rows in a profit and loss spreadsheet and I want to highlight the loss-making rows, I can now pick out the items that, according to, again, any Wolfram language computation of anything to do with the values in that of that item. And as you might guess, the row value function is the same kind of thing, but it works in a whole row at a time. So here I'm coloring the whole row if the profit key is less than 0. So the same essential condition, but I'm applying it to the whole row. So again, this can work out on any styling, font size, backgrounds, font colors, the frame labeling, all of those kinds of things can be controlled either in a fixed, cyclic, or conditional way, making presentation kind of easy and pretty now. Okay, slight change of pace. You've got the data. You can process it in all kinds of ways. What do you do with data? Well, one of the things we focused in on this time is issues to do with when you have noisy data, which is smoothing and fitting. Now we've supported since way back in the beginning the very standard things that you would do for data smoothing. So you can do things like moving average or moving median or other moving filters on data, and you can fit lines to data. What we're doing is now adding in a couple of localized versions of the same kind of concept. So if I open up some data here, here's my noisy data. We could do moving average on this in order to kind of cancel out the errors. But moving average has a tendency to blur features at the same time as squashing the noise. And what we have now is local model fit, which generates this fitted model. But basically, it is the fitted model is something that behaves like an interpolation function, but it's sort of based around a bunch of resamplings that gives me the underlying trend of that. And you can see it's sort of doing quite a good job of preserving bends that happen to be in the data at particular points. And it also comes with other advantages that it has, for example, uncertainty around it. So if I find what's the trend at position 1, it's not only giving me the value, which is 0.716, it says, but it's giving me an error bound on that as well. So what this is actually doing, something called local adaptive regression, or LOS fitting is often, or LOS fitting is it's often known as. And effectively what it's doing is it's taking short intervals, fitting a line to that, taking the midpoint of the fitted line and taking that as the estimate of the trend. So it's a little kind of sensitivity window of what kind of interval it fits that line over, but it's repeatedly fitting short lines and then taking the midpoint and treating that as the best estimator and taking the error bound from that. It works in higher dimensions, so we can take noisy data that we're doing, say, in this case, a contour plot on, and do a local adaptive fit on that to give me the denoised version in 2 dimensions. And again, it supports error bars on that. The other thing I said was fitting. And the problem with fitting is that you have to have a model. So that's fine if you know your model is we're fitting a straight line, or we know this is a nominal distribution of some data. But if you don't have a model in mind, you're kind of lost with fitting. What kernel model fit does is it breaks this into a piecewise fitting problem effectively. So I'm going to, for illustration, I'll use linear as the model that we're fitting to. And what you can see here is it's broken this data up and fitted separate straight line fits across different sections of the data. And there's a range of models here as well. So we could put something here like Gaussian, and you won't be able to see the joins now because it's a smooth model, but it's effectively doing the same thing. It's fitting a sequence of Gaussians to different sections of the data and joining them up. That gives us the advantage now of we actually have a model, so we can get the equation out of that model. And it also gives us, again, uncertainty around any given point. And in fact, I think we can get an uncertainty model as well. So these are kind of just more powerful local versions of basically of moving average type smoothing and line fitting, but these are powerful techniques for real world data, for preserving features and dealing with things that don't have a simple underlying model. Of course, in the data world, there's always new formats. So there's a few new formats here: common log and extended log and JSON lines. These are all sort of logging formats. AVIF is, I think, an image video format. We've extended some of the existing formats to be able to import efficiently and directly into tabulars. And we've speeded up a few things I've already mentioned, Markdown. We're now at over 280 file and serialization formats that are supported for import and export. Something we introduced in 14.2 that is now sort of coming of age and becoming useful is data connection object, which is really just a simple unifying way of representing an external piece of data so that you can use it directly just as a kind of symbolic pointer. So while a lot of things you have a URL to point to data, very often you don't have a URL. You have to provide all kinds of connection and authentication information, maybe a select statement in a database. And the idea is to package all of that up. So we now support databases as backends for data connection object and a couple of services like OneDrive and Kaggle. So by way of illustration, actually, I seem to have already run this in this notebook. If I rerun it again, I'm now reaching into Kaggle and I'm saying I want to connect to Kaggle and get this particular data set from Kaggle, which is whoever Joe Beach Capital is, has provided the top 10,000 Spotify songs, and I want to bring it in as a tabular. And so in a completely transferable way, I'm able now just to give you a reference that I can run and fetch that data in dynamically. And of course, this is a tabular, so I can do things like histogram a column of that directly. So there's the distribution of danceabilities of those 10,000 songs from Kaggle in 2 lines of import and visualize. But very much just a plumbing exercise for elegance and convenience. Okay, another mainstay of Wolfram language, of course, is all kinds of beautiful visualizations. We've been doing a little bit of work here. The first is actually around the things I've just been showing you, which is as we've been improving model fitting and data smoothing, one of the workflows that's come up on the list of things to improve was a really standard thing that lots of people do over and over again, which is you've got some data, you want to fit a model to it, you then want to plot the data and plot the model so you can see the 2 side by side and compare. And we've made that now a single step exercise. So there's this new visualization command, list fit plot. And in this case, I'm just grabbing some air temperature data on Champagne over a period of time, which is, it's actually grabbing the data that's taking the time here, but hopefully in a moment that will come in and you'll see what we get. Hopefully. There we go. So in a single function now that takes just the raw data, I've achieved both I've done the fit and the data and plotted the 2 together. And in this case, it's handling data objects automatically over the X interval. And there's a bunch of ways you can control that. You can control the model for fitting. You can decide what elements you want to see. So, for example, you might show that same thing without the data, but with the upper and lower bound 95% confidence intervals. It works in 3D as well. So here's an equivalent in 3D with, again, I'm asking here for the band surfaces, but in 3D, there's a new little kind of visualization featurette here, which is that when you've got 3 surfaces going on with some transparency, it gets a little bit confusing to see when you're seeing through and how close they are together. So there's this new feature of band of pillar points where just little pillars are put in between the surfaces to give you a sense of how close the surfaces are when you're looking through a surface. So we can see here, even though we can't quite make out the underlying surface, we can see from the very small band pillar that surface is quite close over there and increasingly close as we get to the corner. There's a new just filling in a very obvious gap in the space here of, if we get the accidents data back in again, smooth date histogram. We've had smooth histograms. We've had date histograms, but we've never had smooth date histogram. So now the ability to take that data and give a joined up smooth version of the density of values. So we can see here, regardless of the severity of accident, we can see that there were a dip in accidents in London during April. I guess that was Easter, and during the summer when everyone's on holiday. But otherwise in that year, the trend was generally upwards without having to do the bin counts and a smooth histogram of the bin counts. Now this one's getting into the details, but it's the kind of thing that makes a difference between sometimes a presentable, publishable plot and an unpublishable one. If I pick on feature space plot, but this is a general thing across lots of plots, here's a typical labeling problem. There's an awful lot of points in this feature space plot of flags and how similar they are. So you can't label, well, you could label all of them, but it's made an automatic decision here to label some of them to give you a sense of some interesting points that are in the extremes or in the middle of that set, and has decided not to label things that are close together. Up to now, that kind of labeling was either you had to explicitly write a labeling command for each data point, and you might write some code that would map that over all of the points, but you had to take control of each point, or you had to accept what feature space plot is doing here, which is automatically doing it. And we've now filled in a middle space where there's this labeling target function, which takes all kinds of parameters. One of the simplest is to say all, which is a way of saying I want to label every point in that. So we're going to get a rather jumbled plot here, but everything has been labeled. Maybe if I zoom this in enough, that would be useful. Or I can provide all kinds of parameters. So I can say, for example, I want to label 3% of the plots, try to avoid overlaps. And here I've kind of turned down the density of labeling to approximately 3% of the points have got labels on. So there's various things you can control here about maximum overlap and labeling fraction and other parameters that lets you use automation, but not in a take it or leave it kind of way. In the end, it's that kind of thing I think we need to be doing a lot more of in the Wolfram language, because the more automatic things are, the more useful they are. And in a system as big as Wolfram language, it's that kind of automation that makes 5,000 functions usable without you having to spend hours learning the syntax of every single detail of every function. So yeah, more controllable automation is a key feature. This one's a small but again very Wolfram-y kind of thing. We've had around for a long time. You could do list plots of data points with error bars on, but around has been essentially a numerical function up to now. That it takes numbers, and we can do numerical computations on that. So I could, do a calculation like what happens if I add two of those things. But it's never supported symbolic things, and we're trying to make everything in the language that can work with numbers work with symbols. So what does that mean in this case? Well, now you can have things like function plotting, where the error interval is a function of, well, it could be a function of anything, but here it's a function of the dependent variable, in order to put on things like error bounds onto plots where there is a functional description rather than a data description. And you'll probably see the connection here with the new visualizations and the way that our fitting and smoothing now feeds smoothly into visualization, needs things like around just to generally work more seamlessly, so that these things all join up nicely. And joining up is what we like to do. Again, supporting 3D. So here's a simple plot of x plus y, where the error is x times y, and you can see the error grows as we head towards the top right corner of the plot. Right. Few other things to skip through quickly here. Interactivity has been one of those things that we've built into a lot of the plots for a long time. So as a simple example, pie charts, you can click on them. You may not want that though, because what if you don't want somebody interacting with your document? You just like it the way it looks. Also for efficiency, if you're just exporting the thing to a PNG or an SVG or a JPEG or something you don't care about, generating that interactivity, throw it away. So now we have a plot interactivity goes to false on a lot of plots, where I can click on this, but it doesn't do anything now. It's killed the interactivity. So it's sort of downgrade in a way, but keeping you in control of these things. There is a couple of new graph layouts. So for graphs and networks, there are these two new layout mechanisms that place the points progressively on a Poincare disk. And I'm not going to bother showing it here, but geographics now have new vector rendering, so it's faster, and that's allowed us now to flip geographics to use vector graphics by default. So they'll be crisp and sharp at any print resolution. Already I've started making use of that. If you check out a resource function I wrote recently, it allows you to decompose geographics. So I've got a resource function that says, I only want to plot forest cover and roads. Don't show me anything else. Or I only want the buildings to be shown in this plot. Or I want to style buildings red and roads in green. And you can now control those things, because the default graphic has got lines and polygons in it that have semantic labels, rather than just being bitmaps, which was our default before. So more powerful, but also mainly higher quality. Right, let's go to another topic now, getting a little bit deeper into the system. Geometry. So geometry has been always for us, not just geometry as in angles and volumes and things that you might kind of do mathematical computations on, but it's also our representation of things in the real world. So if you're doing things in engineering or anything in the real world, then things have shapes that are not ideal things like circles and rectangles. So one of the things that we've added out here now is new ways to visualize things in 3D space. So when you've got 4-dimensional data, you've got X, Y, Z positions, and then they have values in those. We've had some tools for visualizing those kinds of things with, I forget the name of the function, but slice surface plot. Is that the right function? That takes horizontal or vertical planes through that space and makes individual contours and surface plots on those. We've now extended that to handle any kind of geometric shape. So here I've just taken a sample of geometric shapes, and I've plotted the same function over those arbitrary geometries. So perhaps this is a more practical one of viewing that space as a tetrahedron and seeing the function and how it's intersects the values of that space. But it can be any geometry, so that includes things that you've captured from the real world, like this 3D scan of, I think this is the Phobos asteroid, and I've mapped the same function over that object. And of course, we've done the same thing for that's contour plots. We also have the same thing for density plots. And in a similar way, we've extended the idea of function interpolation. The idea of function interpolate is to take an expensive function. This one isn't expensive, but a simple illustration here, and sample it over a space, and then make an interpolation of that you can then execute on very fast. So the idea is that I can make an interpolation function of this function, but now I can set that sampling to be over any 3D geometry. So I've specifically targeted the sampling to be over the surface of this kind of washer shape that I created, and then we can get the value out at 1.111 in that 3D space from that function, from the fast interpolation, but targeted very deliberately by sampling over that space. And of course, you can imagine that now ties back into these visualizations where I could say surface contour plot that interpolating function back over the shape that it was sampled on, as a quick way of visualizing surface function valuations for things that are too expensive to sample at high quality. Now, the next thing really is more about geometries, but it sort of does relate to real world as well, which is shortest path computations. So we've had shortest paths in graphs, where you're trying to find the route over a network that is the shortest path around or between points. We've now extended that to the geometry setup. So by way of illustration, here's the simplest example I can think of. I want the shortest point from 001 to 010 on the geometry of a sphere. And as you imagine, it would be a straight line around the great circle that intersects those 2 points. And we can do computations on that with the shortest curved distance. Because this is an idealized shape, we can actually work that out exactly. So that's pi by 2 is the arc length. But this is any geometry. So we have the whole language of being able to take the unions and intersections of idealized things and taking mesh geometries from the real world. So here's a slightly fancier example where I'm saying find the point that's nearest on the mesh to the 100, so the top, and nearest to the right-hand side, and then find the shortest curve that joins them. And that's a kind of direct way of saying, take this rabbit and find the shortest path from its tail to its ear. So if we're looking at optimization, sort of slicing type problems, or here I'm doing a problem I tackled in the Wolfram blog many years ago using kind of image processing techniques, I can, sorry, run that again. Then hopefully we can find the shortest path through that, the geometry that represents the converted image into geometry space. So it sort of fits with things like robotics problems. So you need to plan the route for a robot across a network or around a factory space with objects in the way, find the shortest route that it can fit through to minimize its journey time. Those are all kind of geometric shortest path type calculations. Another bit in the pure kind of geometry side of geometry is curvature computations. Let's make a quick geometry. So here's a random geometry I've made. What's the curvature at a particular point? I don't know which vertex is number 1, but how curved is it somewhere? Well, as you can imagine, it depends whether we're looking from this angle or this angle. One's sharp, one's flatter. So we have these new commands: region max curvature, region min curvature. Well, actually, I've made a poor example here where it's symmetric on that point. And there's also region Gaussian curvature, which takes a sort of into account saddle points and convexity and concavity, which is better to understand on something smooth and continuous here, that you see that Gaussian region Gaussian curvature has a high positive value on sharp convex points. It has high negative value on saddle points and 0 on saddle points, and negative when we get into concave areas. So properties of geometries that you can compute with. Now the next bit is back to joining with the real world, that when you have real world shapes, you might be able to take those things from things that have been previously mapped, like maps. But very often you're trying to process things like scan point data. And for a while, we've had the ability to construct meshes from points. We're now building out the mesh processing with better quality and repair. So being able to simplify, resample meshes, smooth meshes, fill in holes and pathological points, and further smoothing. Let me just kind of give you pictures to help you understand what those are doing. So here is a typical bad mesh problem. I've gone back to my bunny, but in this case, I've got dodgy data coming in from my LiDAR that is full of some kind of random noise errors. So the idea of smooth mesh is basically a kind of moving average type solution to cancelling out noise by looking at neighboring points. So that's a smoothing. Simplified mesh tries to not change the mesh any more than it has to. So that's pretty close to the same thing. But if we look at the actual mesh count between those two bunnies there, you see the simplified mesh has only 10% of the polygons of the other one. So it's a downsampling exercise to give you the minimum amount of data for fast computation, but minimizing the loss of integrity of the shape. So it's throwing away points, meshes that are very similar to each other in favor of ones that have high curvature and therefore more important. If I make a really overly simplified one, then you'll see, so here I've deliberately oversimplified it into a almost hardly any data left. Subdivide region is a little bit like smooth mesh, but it's more trying to invent meshes that aren't there rather than average out. So it's doing sort of adaptive recursive subdivision to try and extrapolate from what it's got into something that is a smooth reconstruction of the original. So much smoother, but there is a certain amount of guesswork going on in subdivision region that's trying to reconstruct from low quality. So it's slightly different purpose, but they're all in the area of we've got point meshes and we need to fix them and make them easier to process. And obviously anything where you're dealing with kind of point cloud representations of shapes, those things become relevant. So anything that where you're sampling points or you're using things like LiDAR or other kind of image capture to geometry type tools. Okay, I've put this down the list, even though I think actually one of the things is kind of quite profound as a paradigm. So in the machine learning and Gen AI, this is all really Gen AI related functionality. And the top of the list is a new mechanism for orchestrating LLMs. I haven't listed it here, but we also have support for a whole bunch of new LLMs, including local LLMs. So you can now download things like Ollama to your local machine, and the functions like LLM synthesize and LLM example function, they will work without sharing any of your data to remote services the way they have in the past. So probably worthy of being a point is local LLM evaluation. They're not as powerful, these local models, and the bigger ones, you need some pretty serious hardware to run them on, but they're local. So there is no per query cost apart from electricity and CPU time. You're not paying a provider for them, and they are privacy oriented because you are hosting everything. It's all local to you. But LLM graph is really how you orchestrate what you want the LLMs to do. And you know, the buzzword of today is sort of agentic, and in some people's view of what agentic means, it's sort of multiple LLM agents doing different bits of the job and working together in a team. And that's what LLM graph does, is allow you to orchestrate chain of thought and independent agents doing bits of a problem. So here's my simple example. I've got 3 agents in this sort of agentic language: Poet 1, Poet 2, and Judge. And each have their own role within the process. Poet 1 is going to write a short poem about summer. Poet 2 is going to write a short haiku about winter. And then the judge is going to take the output of the output of Poet 1 and the output of Poet 2 and decide who did the best job amongst those. Now, if I can give you a kind of sense of the relationship there if I load that up. So we got 2 input nodes and an output node. But there could be any number of inputs and outputs. It doesn't all have to lead down to a single output. We might have a side thing that is a précis or something that is another output. In this case, I'm going to call it and say I just want the final outputs. which will be the judge. And you'll see it briefly here, computing nodes poet 1 and 2 in parallel. 2 finished, poet 1 is still thinking. And now the judge is acting, and we get its conclusion. And it's actually refused to judge, which is very equivocal of it and very LLM-ish. I guess I needed to improve this prompting that says, I insist you choose one of the best and use whatever criteria you want, something that would force it into a decision. So slightly disappointing results in this occasion, but several features there. You could see that the kind of the scheduling was all automated, that poet 1 and 2 are independent in the graph, so they could happen in parallel, and the judge couldn't operate until both 1 and 2 were in. And it also deals with things like if there was a vertice here that was the précis, the poems, but I didn't ask for the précis, then it doesn't waste time computing the output that nobody's looking for. So it's intelligent about the orchestration. And these things can be arbitrarily complicated. So here's a slightly richer example where we are going through a decide, review, rewrite, and present stage. So we've got some input, and the decide node says, is there something wrong with it? This dotted line shows it's a conditional thing, so it might just terminate there. So it's effectively a LLM-based if statement. The review says what's wrong with it. The rewrite says rewrite it correctly, and the finalize says summarize what's happened. And you can see here that these are just agents in that same sense. But the review one is using Wolfram language code. So we actually have different kinds of, you can see from the coloring that there are different kinds of nodes that can mix decisions, LLMs, mappable LLM, and Wolfram language code, and you can describe the whole flow of that knowledge through the graph. So now hopefully this one works a little bit better. We can give it correct flow, and it's on the decide step. It decided there was nothing wrong with it, so it terminated. Whereas in the correct flow, this time it says decide, it decided something was wrong, it reviewed it, it's rewriting it, and now here's my summary that here was the input and here was the output after being rewritten. So you can now take control of the breaking the problem down rather than hoping the LLM's intelligence, for lack of a better word, will know exactly what to do. You can break the task down, control it more finely about what happens at each stage. You can mix code and LLM in order to make really rich decision-making processes. In a way, what's gone before is, this is the generalization of. So those who have been using our LLM tools, LLM tool is a bit like the Wolfram language vertex. Well, it's really like an LLM graph that has a decide if the tool should be used and then run Wolfram language and then put the two together. And LLM synthesize is like one of the LLM vertices in this. So it's sort of bringing it all together into one rich workflow with all the power of the graph theory to analyze the graph for dependencies and ordering. A couple of smaller things. We added the idea of semantic indexes. This is if you're doing what people think of very often as RAG, which is you index all your PDFs in your knowledge base with a semantic index. So when I search for a particular phrase, you can find the document that appears to answer that, and then you can hand that to the LLM to read and summarize, or you can just return the document. You can just treat it as search. So we've now exposed more internals of semantic ranking, the function it depends on. So before, semantic ranking could tell you which of these words were, these words was most like fish, but now we can actually return the level of match, as well as the rank, as well as, in this case, I want all of them. And we can see here that tuna is the highest rank match, but we actually have the relevant score. Now, the reason why that's useful is there's also a new option, semantic search re-ranking, and that allows you to use semantic search to find relevant documents, but then use a supplementary test to decide how to return the final list. So if these weren't words but were documents, then maybe my search was, how do I buy Mathematica? And it goes through all of the web pages that we've indexed on our site and says, well, there's the store page, and there's the licensing page, and there's some other page that is how to buy extra credits or whatever, and they rank like this. But then I might re-rank by saying, but I actually want to give more preference to a newer page that's got the last change date more recently. And by being able to combine the relevance, I can weight that against date. So I might just say, give me the newest page out of the top 4, but I might say something that is more than a year old should reduce the relevance by 10%. well, something like price, then they would probably reduce it by 100%. Maybe being more than 6 months old would reduce it by 20%. But the ability to weigh up relevance against other criteria, like the length of the document or other things like that, you need to have the relevance score to be able to make your kind of own re-ranking. But it basically, in the end, it's for implementing search, and this allows you to take more control over how you rank search results when you are using create semantic search index as your mechanism for doing search. Okay, got a long time without any kind of mathsy things. So I'm going to skip through this quite quickly because they're mostly areas that you will either recognize and care about or don't recognize and don't care. So I'm not going to go into too much detail. Since the very first version of Mathematica, we had a command called non-commutative multiply, which was really a placeholder that did nothing, that allowed you to add your own rules. Well, we've now built out non-commutative algebras. So these things come up in all kinds of theoretical subjects. So in things like quantum mechanics and in kind of geometry calculations. So these are algebras where A times B is not the same thing as B times A. And we can treat that very generically and say just everything is non-commutative. But in this case, I'm doing a slightly more interesting algebra. I'm setting up an algebra where everything is non-commutative except for the symbol C, which does commute with other variables, and S, which is a scalar. Every other symbol is going to be treated as non-commutative. And now I can say, take this expression as a new, there's a new special character for non-commutative multiply, but I can type star star like I could in the first version of Mathematica as well. And I'm saying expand that operation respecting the rules of commutativity and non-commutativity that I've declared in the algebra. And here's the expression. And you can see there's a range of algebraic operations like Grosvenor basis and simplification and generalized versions of power that can operate on these kinds of algebras. So a whole new area of algebra. It's a pretty big deal if that's your bag. We've also built out really some of the just small missing special operations within matrices. Obviously, we've been doing matrices for a long time, and really you've been able to do all of these things yourself. But hey, why should you? So there is a whole set of new standard operations that are doing different kinds of decomputations, different kinds of polynomial representations, projections on matrices, all things that you could probably do in at most half a dozen lines of Mathematica, but they now have their own main functions. And these are all very standard operations that now just work out of the box. We've had integral transforms for a long time. I think there's about 4 main kinds of integral transform, and we've had 3 of those supported for quite a while. Things like Fourier transform being a very popular one, and Laplace transforms being another. And I'm trying to remember the 4th one, but the one we've been missing for a while is Hilbert transforms. These come up particularly in things like signal processing, of handling imaginary and complex parts of signal systems. And this is a pretty full, because it sits on top of integration, which of course is supremely powerful in Wolfram language. Then we can now basically do essentially most Hilbert transforms that you might expect to be solvable are done now in a single step with this new Hilbert transform operation. Another space we're filling out, or just about to finish filling out, is special functions. We already have by far the biggest collection of special mathematical functions, and we are kind of running out of special functions that exist that we haven't got in the Wolfram language. One of the last to be added is Lommel functions. These things come up in things like diffraction patterns and optics problems. So like every other special function, we have a full implementation. So that includes real numbers, high precision arithmetic. It includes exact arithmetic, where those things are known, and it includes things like complex number arithmetic, again, and complex number arithmetic at arbitrary precision. So I should have pre-evaluated this one. It actually takes a little while to compute, but in a moment we're going to get a complex 3D plot of the real and imaginary parts of that function over the rectangle from plus or minus 3i and 3 in the real domain. Another area that has been a recurring story is PD modeling that we continue to build out. We built a solid finite element solver that handles a really broad range of PDEs. And for the last few years, we've been building out a higher level language for representing things that the particular PDEs that come up in different domains of mostly engineering, but also sort of physics domains. So in this release, we've got new high-level constructs for time dependency in electric circuit modeling. And in solid mechanics, we had stress measure before, but we only had one stress measure, and there's various different concepts of stress. So there's a whole bunch of new stress measures that we can compute for solid mechanics problems. And I brought one example with me, which is in fluid dynamics, axis symmetric systems, because axis symmetric is a whole class of problems that we've been building out in other domains. And that is where you have a problem that is a problem in 3D, but fluid dynamics is one where axis symmetry comes up quite a lot, because fluid dynamics often happens in pipes. So here we've got a pipe that goes through a constriction and then into a fatter pipe. But there's an axis that it's got symmetry along. It's round. So we can, in fact, consider this as being a two-dimensional problem in terms of the right-hand half of a slice through the pipe. So here's the thin part, the constriction, and the fat part, and solve that in a generalized two-dimensional way. And that allows us to solve it much faster and more accurately, and then visualize that or compute with that generalized back into the 3D. So that vortex that we computed in the 2D slice, that generalizes round into 3D. So for problems that can be considered in this axisymmetric way, we now have axisymmetric methods for quite a few of these different physical domains, fluid mechanics being the new one. But in the end, these are all pretty obvious things that if you're doing sort of multi-physics and engineering type things in the real world, then it's all about having a higher level way to describe them and then simulate the PDEs that underlie the behaviors. Zooming back out something that's a bit more accessible if you're less technical, video processing is something we've been building on top of the image processing for a while. The most exciting thing here is I'm doing slightly backwards because video stabilization is kind of very accessible thing to look at. Let's run this first of all, and then I'll explain what happened. But it's actually a special case of a more general and more useful underlying feature that we've added, which is feature tracking. And the idea is that we've got, I'll show it to you in a moment when it's finished computing, a handheld video here that, like a lot of handheld videos, is a little bit shaky. So in a moment, it will have hopefully computed that. And now just processing the final video. And we can show the before and after. So the before here, very bouncy, shaky cam action. What this video stabilization has to do is to lock onto something that it thinks is representative of the frame, crop the frame slightly and adjust it so that those points remain stationary. And then after stabilization, you see all of that vertical wobble has been removed and we've got a much smoother video. But I think actually the underlying mechanism is more important, and that comes in a much more generalized feature tracking function. And I'm going to just grab one of the frames of video here and start this processing. I picked some arbitrary point here. It's like, what if we didn't care about watching the video? We actually care about what happens to something in the video. So in this case, maybe I want to, I'm choosing a flight path for a drone, and I want to keep focused on that space between the trees. So I've picked it here just by coordinate value, but I want to track how that moves. Similar problems would be, well, what if I'm doing ecology and I want to track the flight paths of 100 birds in a video? Then I want to have 100 start points, and I want to see how those points move independent of each other through the frame. So anything where you're analyzing objects within the video, security being another good example. Here's a person of interest in the crowd. Where did they go when we handed them off from one camera to another? Can we track them from frame to frame? So here you'll see my purple dot here has tracked the white space as best it can figure. Even though the shape of the space has changed, it's doing its job to track that. And we can track an arbitrary number of these from start points. Previously, we had image feature tracking only for things that had semantic meaning in the image. So you could say track things that is a car or thing that is a person. Now, anything that you can put a coordinate start point on, you can track that texture, that group of pixels effectively through the image, and track when they enter the image, when they leave the image, where they went, things like that, with any number of them simultaneously through the video. So anything with flows or movements that you need to analyze within video content, feature tracking is quite powerful. I think we're almost at the end of this next one. Wolfram language aims to be a single joined up thing, not a bunch of random libraries that you have to write glue for. So we are finally filling out the last of the operations that work on images, like things like mean filter, that now if you say mean filter of a video, it will just do the right thing across the whole video. You don't have to write code yourself to map the mean filter command through each of the images on an image extraction of the video. So it's just proper joining up. Right, let's jump back to engineering. And let me get this loaded because I haven't got the system model libraries loaded here. So I'll just run this while I explain what we're taking on here. We have this world of system modeling, the Wolfram System Modeler, that is a framework for building and simulating with large complex systems of components, where components can be dragged from libraries or created from scratch. So a circuit diagram is a classic example. And here's a circuit diagram. I've got some resistors and inductors and a power source, and they're wired up in some complex way. And System Model lets you help design those things. The simulation of those, once they're built, any Modelica model that is compatible, we can just treat as a black box that represents the circuit. So that in the Wolfram language world, this thing is pre-built. I could try and program in the Wolfram language, but it's not really designed for that. And I've imported the model as a black box. So just like I've got functions like sine and cos, I've got circuit. I've got Cower low-pass analog circuit as a function now that I've dragged into the system. So we've had for a while the ability to do things like tune those to fit the parameters to experimental data, to simulate them, to plot how they different parameters behave. What we're bringing here is model validation. So what do we mean by that? Well, we build a circuit, but does it work? Well, what does it work mean? So you need a language to describe that. And the language really breaks down at the moment into these sort of 5 paradigms. We want some property to always be true. We want some property to remain in some state. We want some property doesn't have to be true at the beginning, but we want it eventually to become true. And the opposite is we want something to be true until something else happens. And we also want to have a way of playing around with time. So what we mean as from and until can be manipulated. And between those things, we can set up a set of rules that we say the circuit is expected to behave under. So here's my simple example. I've said system model always. So for all time, the voltage across resistor number 2 has to be less than 0.55 volts. So in my fictitious example here, this resistor will burn out at 0.55 volts. So the circuit will fail, the resistor will get burnt out if I ever exceed some voltage that is in the design spec for why I chose to put that resistor there. So we want to know is it safe to assume that this resistor will never exceed 0.55 volts? Well, that can potentially be a very complicated simulation exercise. It's gone away and it's run a simulation. There's various ways of doing this with Monte Carlo. So here I've taken the simplest thing, which is just to start the simulation with its default values. But I could say throw in a million different start points that we might sample from experimental data and say, how often, if I have temperatures of the day, maybe I want to throw it at the historical temperatures for where I'm sat in Oxford to see the different conditions it might be under. But here I've just said run it once, and it said it's failed. Out of one simulation, we had one failure. It succeeded none of the time. And there's various properties we could look at, but I'm just going to throw up a plot here that says, show me visualizations of the failure. And you can see that most of the time it was in a pass state, but between seconds 9 and 10, it was in a failure state. And if I actually run the simulation, in this case, it's really easy to see what's happened. Here's my voltage in this oscillator circuit, and briefly it overshot the design condition before stabilizing underneath. And this was what the failure measured. So in a simple thing like this, I would have gone straight to the plot and looked at it and gone, oh, that's gone too high. But in a complex system that's, trying to validate an entire car to say, will this car behave and anything go wrong over thousands of conditions, you can imagine it's impossible just to look at the model and say quickly, is it valid? So now we have a whole language for automating that process. Still in the kind of engineering space, we've got a little bit in control systems, mostly aesthetic. So where we've had various control system representations like state space models, so these are things like simple controllers and for kind of creating stability in the heating of a shower, for example, might be a feedback control system. We've made it just easier to take this object and immediately look at it and say, well, there's some standard visualizations for this. So maybe I'll just click on this pop-up tool that appears underneath and see the impulse, the step, the singular value plot, the Nyquist plot for that thing. I can click on the properties bar and immediately see some of the key properties. And I can switch between different visual representations of the thing and different types of representation instead of as a matrix view. So there's the key properties. So really just a convenience thing for quick interaction. Those properties are also now available as down values, so I can just reach and say, give me the output matrix for that. And there's one new visualization, which is not a terribly exciting visualization, but a pole zero plot is a quick way of being able to tell whether a system is stable. If you're a control engineer, you'll look at this and go, oh yeah, that's a stable system because the poles are all on the left on the negative X direction. Very much control theory stuff. I'm a little bit over time, but I'm going to press on here. And I think we have I've got 2 more sections to do. So let's just try and go light here. We have had molecule visualizations for a while, but now those have proper color controls, both in a manual way, but also I'm doing here in an automated way to say color that according to some property of the molecule that we're visualizing. So I can color by properties like oxidation state or bond length. So now these colors actually mean something. Or I could roll up my sleeves and say, okay, I want to color this particular thing red and so on, before you just kind of take them in black and white. Protein folding is something we've had for a while, but you might not have noticed that when I fold a sequence and figure out how it will optimally be folded in 3D geometry, that was using an external service. Now, for potentially performance and privacy reasons, there is this option method goes to local, which will download a neural network and run the model locally without sharing any of this, what sequence you're interested in remotely. And to go with that, there is also better ability to compare these things. So in this particular case, this is not a theoretical thing. This has been studied. So here I've done a automatic fold to compute the folded version, but I could also downloaded the experimental data, and you can see at a glance they look similar. But if I look at the plots together, are they similar? Well, they're on a different space, so it's hard to know. We now have biomolecule align, which will basically optimize the orientation and scale of those things so they can be shown together. And we can see actually they're really good alignment until you get to the very ends where they seem to diverge. This little strand at the end, the theoretical version and the experimental version diverge, but everywhere else it's been a pretty good attempt at doing that. And sort of in a similar space, we now have a molecule feature distance function that is available to immediately say, for 2 molecules like benzene and TNT, a kind of numerical comparison to say how similar are they molecularly. Obviously, you can roll your own, but it's nice to have one that's out of the box. So as a more kind of practical example, I'm going to search all of the alkanes and say which one of those is molecularly most similar to ethanol. And hopefully, maybe I didn't download the alkanes on this machine before. We will get an answer that is the most similar. And I'll skip the clustering example where you can take a whole collection of things and build a kind of dendrogram type clustering. So here we go. Propane and propane 113C are the 2 that are most similar out of, I don't know how many alkanes there are. There's about 20 or 30 of them. And I'll leave that clustering running for a moment, which also takes a few seconds while I explain the compiler. And then we, I think, are done. So the compiler is a long-term project. I've talked about it in previous things because there's a steady ongoing effort here to be able to take the benefits of the Wolfram language, which is here's our clustering that says L-aspartic acid is most similar to this L-aspartic something else, aspartane, which are then pairwise most similar to L-serine and so on up the tree. Now, the compiler tries to take the benefits of the high-level, loosely typed, very rapid prototyping nature of the Wolfram language, and allow you to then write code in that, but get the benefits of performance of compiled languages. So you mark up your code with typing information. This is going to be a real 64, and it's going to take that and look at your specific hardware. So not just that I'm on Windows, but I'm on Windows with an Intel such and such chip, and compile optimized code that will run directly as assembler on the chip for very fast execution. That's the basic idea. Now, it's very much been a sort of coders thing. If you kind of come from a C background, this kind of stuff is really familiar. One of the biggest things we've done here is actually write a proper tutorial now. So it was documented in how the functions work. But if you're wanting to understand all the concepts, we now have what amounts to a small book on how to use the compiler. So if we jump into some random thing like here, generating raw low-level virtual machine code, there's a narrative here of how that works, what you do, and there's some pages on LLVM. So you see the whole thing adds up to a couple of hundred pages. So now if you want to get into this, the onboarding is much simpler, and that's been quite a significant effort. If you're not one of those people, let's jump to some functionality. And I haven't loaded the compiler, which is still an ongoing project to make the compiler itself load and compile faster. But no, it is loading here. So this will be slow the first time, but the second time it will be much quicker. But let's explain what this thing does. So typically when you write a piece of code, it runs and it finishes and then you're done. But there is a program paradigm, which is sort of incremental functions that you run and you interrupt at some point. You get some value out, but you want to have a preserved state. You don't want it to work to get into the state. And you want to go back to it later and say, now give me the next answer, or compute more on this solution and give me another iteration. So while some of this is kind of compiler infrastructure here, function compilers using compiler, here's the typing. These are features of the compile only. The two new things here are incremental function, to say it's one of those functions. That takes care of all of the bookkeeping. And incremental yield, which is how we say when we're going to stop. So my raw code here is while true, so an infinite loop, take some number and add to it another number. So ordinarily that while statement would be an infinite loop. It would just keep adding num over and over again, and this mul would grow and grow and grow. And maybe I'd have some stop condition, it would stop and we'd be done. But by saying incremental yield, it'll suspend that. And I already compiled it. I've compiled it again. So I'm going to make an instance of that. Add number is our incremental function, and I'm initializing it with 7, which is going to be our num. And we've created a data structure. And now when we say next, it'll run that until it hits its incremental yield, and it'll yield the result. So we added 7 to 7, we got 14. If I do next on the instance, I now pick up where I left off and get back 21. Now, you could do this in the Wolfram language before with global variables. But you'd have to think, well, what variables do I need? What's the state? I'd have to have some code that says, if this is a new instance, then create the state. If it's an old one, store the state in $global state or whatever. And then we've got to worry about what if I have 2 instances of this. So I'm going to create a second instance, which is adding 3s. And now if we run this, we'll see each instance adds 3. But my original instance 1 is still in its state of 21 and is adding 7s. So we'd have to worry about how to make global variables that store the values. We'd have to think about how to pick up the values, how to continue. All of that's handled automatically by virtue of the wrapper and the yield. So certain things where you're kind of wanting to find the next state of something, or you want to do further work on something, are now really elegant to program within the compiler framework. So that's just a kind of nice programming paradigm. I'm going to skip over these. There's some newly compilable functions and a whole bunch of other performance and improvements in terms of things that were in compiler, but I will overrun if I don't stop now. So that's been quite a lot for a few months' work. Just to recap, what we've seen here is a few front-end things, quite a lot in data and visualization, particularly things like smoothing and fitting, a whole bunch of things in geometric calculation. We've got this new orchestration for generative AI with the LLM graph functionality, a whole bunch of new sort of deep core maths functionality, a whole lot of engineering things this time in system modeling, controls theory, and PDEs, and some performance things in the compiler, which of course feed back into the system as a whole. We are one of the biggest consumers of the compiler ourselves. It's what makes things like tabular really fast. So further reading, there's Stephen Wolfram's version on his writings. He gives a little bit of a more philosophical view on and some of the backstory. And of course, there is just a pure list of features at reference.wolfram.com. If you just want to see the new features in an alphabetical order by function name, then that's the best sort of raw list, and you can download this notebook. Quite a lot to have said. I hope that's been exciting. Don't forget to come back for the follow-ons where the real experts who've been working on this will talk much more deeply about the things I've glossed over in a few seconds. Let's turn my attention now to the Q&A. Now's a great time, if you haven't asked a question, to chuck one onto the queue. Are the error bounds one standard deviation unit? They actually come out of the underlying model fitting capabilities. I believe you can control there's I don't want to say for certain, but I'm fairly confident that they're in the same way that when you do this within things like nonlinear model fit, that there is a parameter for confidence level. You can set the size of those error bars. So you would insert somewhere, I think it's a string argument, as an option, confidence level goes to 0.99, and then those bars will get wider instead of they're defaulting to 95% confidence interval, which I guess is not one standard deviation. 95% is probably not too dissimilar, but it's 95%, I think, is the default that they set to. Is there an easy way of showing the fit function together with the graphics when using list fit plot? So list fit plot can also take a fit function. So it's kind of least argument way of doing it is just to say list fit plot of data, but you can say list fit plot of data comma fitted model, and you can make it back into a two-step operation. You're still not having to worry about the show one plot with the other plot. It's still a single plot, but you can say do a fit of model, and then you would do list fit plot of data comma model comma plot label goes to model, and that would allow you to put the model of X would allow you to put the model into the into the plot label on the legend or something like that. The local LLM I know uses localhost by default. Can the local address and port be changed? You know what? I was just talking to my team about this an hour ago, as we were talking about a project that might use Llama, and I don't believe that has been implemented. I am certainly already going to, when a team comes back and says if it can be done. If it's not, I'm going to add it on as a feature request, because I would certainly like that as a convenience away. But you can certainly, of course, use like a service model connect type connection and call the API functions raw. But then you have to know the URL execute will happily call a port and a IP address that you're hosting it on, but you have to now decide what are the parameter names of Olama compared to something else. And we've done that work, so I would hope we expose it, but I don't know the answer to know whether there's a direct way or it's a wait for that feature. I'm going to demand it, whatever. What colors when printing to PDF are changed in 43 and so on? I'm not sure if there are any mappings on conversion to PDF, whether PDF has a kind of color palette mechanism. But if you're talking about what colors have changed generally, I don't know the list, but I know things like, for example, contour plot and list and density plot have had their color functions tweaked. I think Stephen's blog lists some of the individual ones that have been changed. All of those things where we tweak colors, there is usually a color function goes to legacy if you want to force it back into the previous colors. And I think there might even be like a legacy somewhere for the old version 3 colors if you're still going back that far. We probably obsoleted that by now. What about preserving state between sessions? So there isn't, I'm not aware of any plan to make this automatic, but it's not fundamentally a difficult thing to do if you are willing to accept a certain amount of overhead. I can imagine a resource function fairly easily to do this, that basically what's your event to store state, because there's a $post function that you can attach to every notebook evaluation you do. There is also a notebook event action option for notebooks that can trigger an event when you close the window. And both of those could be used to trigger a dump save command, which is dump save without any arguments will dump your entire system state into a file. And then it would be a fairly easy thing to extend initialization to say, if this file exists, put up a dialog and reinstate it, or just reinstate it. So, you know, if you send me email, I'm easy enough to find my email. If you Google me, I can walk you through those steps to do it yourself. But I'm not aware of, you know, I'm suspicious that that might be one of those things that's just kind of annoying and wasteful as often as it's useful. But the core ability to store kernel state is dump save and has been for years. Yes, so somebody's commented Mathematica used to have that a couple of years ago. I'm not aware that it's been taken out. Let me just look it up. This is the command that we're talking about. So dump save, does it take a 0 or 1 argument form? It doesn't document that, but certainly it's got context. So since most of what you do is going to be in global, dump save global backtick is going to dump all of your session variables into a binary file. Dump save is also the fastest way to save state by far. So compared to exporting data that you've got in a variable to, you know, to a CSV or whatever, and then re-importing it, dump save will save the actual state of the variables in the context. So that's the command to look at. Is regression of independent parameters with independent errors supported? I do not believe that is supported within those 2 new commands that I've just used, but the functions you want for that are generalized linear model fit and generalized nonlinear model fit, and they allow you to control the somewhere down here in the documentation there is control of you know, maybe it's one of the parameters. You can control the error model that's going on. I don't use this function very often. There is somewhere in there you can control the model that describes how errors are distributed. So I think that's the thing to investigate. If you can't implement what you're doing through the various options of that, then the answer is probably no. Oh, I mean, automatic preserving a state like Excel does. Do you mean basically automatic notebook saving, where it's the content of what you're looking at that's being saved rather than the computed kernel state? Again, we don't have a good solution for that, and maybe that one is something that is, I think, should be higher on the list. There are a couple of hacks that you can do. There is a front-end option that will automatically save notebooks every time you do an evaluation. Personally, I find that a bit of a pain. So I wrote a resource function which will do something on a time schedule. Maybe I can just get Chrome up here and show it to you. So if you go to the Wolfram function repository, and I can't remember what I called it, but let's look up things I've written and see if that reminds me. It's called something like set notebook auto save. Set notebook auto save time. So you might want to play around with this. So you run set notebook auto save time with no arguments, and your notebook will automatically prompt to save every 60 seconds. You can set a time limit, and you can kill it with, if it's getting annoying, with set notebook auto save to none. Basically, it just does a control S every 60 seconds, or so you'll want to make sure it's a saved notebook, or the dialog will pop up. But after that, it'll just hit save without you having to remember every period. So between those 2 options, you can kind of hack your own version of notebook auto saving. But what I'd really like to see is kind of background auto saving with recovery, so that it doesn't destroy the save that you've got, but it offers that back to you if you've crashed, or you know, your machine died for some reason. And we don't have that, and I have not seen it on the imminent feature list for the front end, I'm afraid. I am keen for that too. Okay. Well, there's a thumbs up for the feature I don't like, but which is so it's up to you. If you like the front end one that does it every time you do a calculation, that's the. But this one is my one. We seem to be out of questions, and we are probably also out of time. So there's a last chance here for any quick question. Otherwise, I will hand back to Jamie to tell you what's coming up next in our schedule.
Thanks, John. Thanks very much for taking the time to address those questions. Next Wednesday, again, we'll be covering what's new in mathematical computation with Devendra Kapadia and other key algorithms developers, and also the latest in system modeler with Ankit Naik and other math core engineers. So we have a nice lineup for you coming up the next few Wednesdays. We look forward to seeing you. Thanks so much for your time today. We'll see you next time.